Hello everybody! In this video we are going to discuss certain principles which you might remember from previous classes on logic, but which are actually not provable in Agda. So the first one of these is called the law of excluded middle, and it says that for every proposition P, either P or not P is true. But if you read this from our more down-to-earth program construction class without those classes on, then this says that for every proposition P, we can decide if P is true or if not P is true. But that seems highly unlikely if P is something which we don't know if it's true or not. For example, if a certain computer program holds or not, or if a certain conjecture in mathematics is true. So if we try to prove this, so here I'm trying to prove this law of excluded middle, I've introduced a P and we see what we have to do. Then we see that we immediately have to say either left of P or right of not P, right? And the only information we have is that P is a set, so P is a proposition. But we have no way of actually looking at this P. I mean, you could say, why don't we pattern match on it? But if we do, then we just get an error message that we can't pattern match on non-data types such as set. So we just have no way of making progress here. So and there are models of this type theory which shows that this is not true in general. So there are models where this is an empty type. So we have no chance of actually proving this. And here's another principle called double negation elimination. So with our classical classes on, this says that for every proposition P, if I know that P is not possible, not impossible, then P must be true. So not P implies P. And again, if you try to prove this, then at least this time, so here we're trying to prove an implication. So we can introduce some evidence for not P. And now we have to produce a P. And we have some information now, right? But the problem is that we have to make a P. And if we look more closely at what we only have a way of producing something in the empty type, right? So okay, if we could do this, then we could produce anything. But in order to do that, we have to produce an argument of this type, which means that in turn we have to feed a P to this function. And but we don't have any P's to feed it, right? That's the whole point, that we want to make a P. So again, we see that no matter what we try, we're going to get stuck trying to prove this. And again, there are counterexamples, there's models of the type theory where this is an empty type, so we have no chance of actually proving this. So these are called classical principles. And this comes from the fact that these are principles that are valid in something called classical logic. And it's called classical logic because it used to be the standard logic, and it still is the standard logic. But at the beginning of last century now, I guess, mathematicians started to explore alternative constructive logics where these principles are not taken as valid. And these constructive logics are the basis of type theory in Agda today. So these are classical principles. And they have no real computational interpretation, right? Because they promise too much. They say that you can decide P or not P is true, and they say that you can just make up information from no information. But what you can do, of course, if you need these in your proof, then you can just postulate them or assume them. So here, for example, we can prove double negation elimination, assuming that we have the law of excluded middle. So let's try to do this. Okay, so what do we have to do? So again, we have assumed that we have the law of excluded middle, and we have to prove this thing, which we failed to prove before. But this time we have one extra assumption, which is going to make all the difference, right? So let's see. We introduce not P, and we have to prove a P. Okay, so how can we do this? Well, we could use the law of excluded middle to see if P or not P is true. And if P is true, then we are done. And if not P is true, then we have to see what that means for the fact that we also know that not P is true. Okay, so the way to make this additional case distinction on something else is with the with keyword in Agda. So you can say with, and then here I put an expression. So in this case I want to do lem of P. Then I do a new line, and I can either repeat all of this like this, then I do a vertical bar, and I introduce a new variable which stands for the result of evaluating this expression. And then so there's no equal sign on this line, it comes on the next line. Right. So this means that I get one extra thing that I can pattern match on here. So if I load this, we see that I have everything I had before, but I also have this QQ, which has the type of this lem expression. So I call it QQ because the next thing I'm going to do is I'm going to pattern match on it, so the name is not going to survive for long anyway. So I'm going to pattern match on QQ, and I'll see if this lem expression evaluates to in left or to in right. So if it's in left, then that's a P, otherwise it's a not P. So I'll just rename these quickly. Okay, so in this case, we asked the lowest to the middle if it was P or not P, and it said, well, it's a P, so then we can just return that P, right? And otherwise here, we have to make a P, but now we have contradictory information. So we have on the one hand not P, but we also have not P, which is not P, right? So if I do not P and apply that to not P, then that gets me something in the empty type. Right? And now if I wanted, I could do a with on this again and then pattern match on it to see that it's impossible, or I could use the function bot_elim, which I copy this for now, which is defined in the standard library in data.empty, and it's similar to one of the examples we did in the previous video, where we saw that if you have false, then you get whatever you want. Whatever here is just the name for another set. So if I do bot_elim applied to something in the empty type, then I get the P I want. And this was the thing that gave me something false. Okay, so this shows that if you have the lower excluded middle, then you also have double negation elimination. And what I suggest you do for fun is to show the opposite, that if you have double negation elimination, then you also get lower excluded middle. So maybe this is a bit trickier, but it's a really fun exercise, so I suggest you try it at least. And if you need some help, then of course you can ask them at the most. Enjoy.